Non-parametric Bayesian models let us learn more from our data as we get more of it. But these models require an infinite dimensional parameter, which poses a lot of practical challenges. So often, practitioners use an approximation instead. One example is so-called non-nested finite approximation, or NNFA. We provide the first finite sample theoretical analysis of NNFAs, and we check the approximation quality empirically. As a concrete example, we'll be considering topic modeling. Perhaps we want to analyze the documents in Wikipedia or in the New York Times. Each document manifests a number of themes or topics. We want to learn what the topics are, which documents contain which topics, and often the number of topics themselves. Typically, larger corpuses contain more topics, so we want to account for that as well. There are lots of other examples where data is composed of different latent factors, and we want to learn those factors and their number. Consider the dictionary learning approach to image processing, for instance. Here, the data consists of small patches from a noisy image. We want to find a set of basis elements that explain the small patches, which helps us denoise the image. One way to model a growing and random number of topics is with a completely random measure, or CRM. The CRM gives a countable infinity of rate topic tuples at the population level. In the associated figure, each blue dot represents a topic. The y-axis is the rate component of the topic. At what rate does the topic occur in the corpus? The x-axis is a parameter describing the topic. In topic modeling, each topic is an element in the probability simplex. There are 3 labeled topics in the figure. The one about education has rate 1.2, the one about sports has rate 0.7, and the one about politics has rate 1. The countable infinity of topics guarantees that no matter how many topics we have seen so far in the dataset, there are always more that can appear when there are more documents come along. The countable infinity of topics does enable flexible modeling, but it makes inference hard. Computers cannot store or update a countable number of parameters. There exist specialized workarounds, such as slice sampling or collapsed Gibbs sampling. However, these methods are known to be slow in practice. Another common workaround is to approximate the infinite dimensional CRM with the finite dimensional representation, or perhaps a series of finite dimensional representations. In either case, we want to check if this is a good approximation. 2 common finite approximations are nested or truncated finite approximations, or TFAs, and non-nested finite approximations, or NNFAs. The left figure shows the atoms of a CRM in a particular order. The TFA truncates those atoms after a certain point. NNFAs generate rates with IID draws in comparison. They use a direct approximation to the rate measure governing the CRM rather than a truncation. We call NNFAs non-nested, since the finite models of larger order don't contain smaller ordered models, unlike TFAs. There are a number of potential trade-offs between TFAs and NNFAs. On one hand, NNFAs are conceptually easier to use, but TFA nestedness can make it easier to expand models as data grows. Past empirical work has also shown that the 2 methods sometimes have similar performance in practice. Recent theoretical work has shown that TFA models with such a small number of atoms are already a high-fidelity approximations of the target infinite dimensional model. There has not been a similar finite sample analysis for NNFAs. To fill in this gap, we provide the first finite sample upper and lower bounds on the approximation error of NNFAs. From our theory, we conclude that TFAs have better performance for a fixed number of atoms in the approximation. However, we also find that in practice, all of the other approximations, such as approximate Bayesian inference, seem to swamp this theoretical difference between NNFAs and TFAs. Our theoretical contributions comes in a finite sample approximation error of NNFAs. In the worst case, we find that NNFA need many more atoms compared to TFA to approximate the target CRM to the same desired accuracy. Our theory says that for data cardinality n, if the number of NNFA atoms is big K, then the approximation error is at most log n squared over K in general, and at least 1 over K in the worst case. Juxtaposed is past theory for TFA, which says that for data cardinality n, if the number of TFA atoms is K, then the error is at most n times an exponential in K for some alpha more than 0. So we see that in the worst case, the dependence of K on the accuracy parameter is exponentially worse for NNFA compared to TFA. On the empirical side, we provide more evidence that NNFA and TFA models of the same order, K, achieve similar accuracy in practice. The left figure is an image denoising experiment. The goal here is pre-processing noisy input images, like the top right panel, to recover the pre-noise images, like the top left panel. A good denoise image will have high peak signal-to-noise ratio, or PSNR, with respect to the original image. Ideally, we want to use a Beta-Bernoulli model as the prior over the dictionary and have the patches manifest the basis elements. The lower panels are the denoising result for an order 100 NNFA model and an order 100 TFA model. They are very similar to each other. The right figure is a topic modeling experiment. The ideal non-parametric process here is modification of the usual hierarchical Dirichlet process. The x-axis plots the approximation order of NNFA and TFA. The y-axis plots the held-out log likelihood of the topic models trained on the same corpus. As the model capacity increases, both approximations attain higher log likelihood. Furthermore, there's no distinguishable difference between NNFA and TFA. To summarize, we provided the first non-asymptotic error bounds for NNFA approximations of completely random measures. Although we see worse theoretical performance for NNFAs relative to TFAs, our experiments show that both perform similarly in practice. We believe that the approximation error due to variational inference or Markov chain Monte Carlo swamped the approximation error for the CRM itself. Thank you for your time. The next 2 slides are references for additional reading.